Hello, my name is Fanner Fehrmann, and today we'll be going over Chapter 7, which is plane waves, and problem number 3. This problem has 4 different parts, and it gives us an E field to start out the problem. So the first part is determining the frequency and the wavelength of the wave. So to do this, we need to understand the basic form of E waves. So we get some kind of E vector, which has a direction, in this case, x hat. So I'm just going to write x hat for now. Then we also have some kind of amplitude. In the problem, you see that the amplitude is 2. I'm just going to write this as E naught. And then there is a cosine or sine term, so I'm going to write cosine. And inside the parentheses, we have omega t minus k and some sort of direction, z. So this is a general form of our E fields. Now, in this form, it is important to be able to find the angular frequency, which is omega, and k, because these are needed to solve for the frequency and the wavelength of the wave. So the formula for omega is 2 pi f is equal to omega. We can then rewrite this by dividing by 2 pi on each side, and we have f is equal to omega over 2 pi. Now we know that our omega is the 10 to the 8 inside the parentheses. So we can replace the omega with 10 to the 8. And then we can now solve for the frequency. Plugging this into a calculator, we end up getting a value of 1.59 times 10 to the 7 with a unit of hertz. Now, to solve for the wavelength, the variable used is lambda. And lambda is equal to 2 pi over k. Sometimes beta is used instead of k, but it's the same thing. So we need to be able to look at the E field and see what k is. Because we're going to use the scalar form, we're going to exclude the direction of z. So we end up getting a value of 1 over the square root of 3. That is our value for k. So now plugging that into the equation, we end up getting 2 pi over 1 over the square root of 3. I'm just going to rewrite that 3 real quick. Which ends up being 2 pi the square root of 3. These are multiplied together. And this is the value for lambda, which is our wavelength. So with that, we complete part A of the problem. Now, the second part asks us to define the dielectric constant of the medium. So looking at our formula sheet here on the left, we have solved for f and lambda. We need to find n, which is the index of refraction. So we're going to end up writing f times lambda is equal to c over n. But we want to solve for n because we know that n equals the square root of epsilon, which is our dielectric constant. We need to find this epsilon. So rewriting this equation to solve for n, we have n is equal to c over lambda times f. C is the speed of light, which is 3 times 10 to the 8. And then pulling the values that we found above in part A, we have 1.59 9 times 10 to the 7 times 2 pi square root of 3. Now, solving for this in a calculator, we end up finding that n is equal to 1.73. Now that we know n, we can solve for epsilon. So 1.73 is equal to the square root of epsilon. So we square both sides, so we remove the square root. 1.73 squared is equal to epsilon, which ends up being about 3. So epsilon is equal to 3. That is the dielectric constant of the medium. Now, to solve for part C, the polarization of the wave. We have been taught multiple types of polarizations. We know that there are types like linear. We know there's right-hand circular polarization, left-hand circular polarization. We also know there's the elliptical versions of this, so right-hand elliptical polarization, left-hand elliptical polarization. So we have to understand by evaluating the E field that we are given. So we know that it is not linear because there are two terms, and one is sine, one is cosine. These are not in phase. Well, yeah. For a linear, it's usually just one term. So it would just be like this example of the original E field that I wrote at the top, where it's just cosine. That, for instance, might be a linear. But because there's two terms, one's cosine, one's sine, it can't be linear. So then, for it to be circularly polarized, the phase has to match and the amplitude has to match. However, when we look at the amplitude of these two E waves, we see that they do not match. The first part is 2 for the amplitude, and the second part is 1. So the amplitudes are not matching, so it can't be circularly polarized. So then this means that they are elliptically polarized. Now to determine whether they're left-hand or right-handed, easiest way to do this is to draw out a coordinate system and use our right-hand, left-hand rules. So we will draw x and y as our axes. X, y. And then we need to make sure that we have a proper z direction. So using our right-hand rule, our index finger points to x, our middle finger points to y, and our thumb will point in the direction z. So we end up finding that z is out of the page. All right. Now this is also the direction of k, right? K is in the positive z direction. So k is also in this direction. Just going to denote this here. So k is the direction of propagation. So the wave is moving in the direction of k while spinning around in the y and x axes. So to do this, or to solve for which right-hand or left-handed it is, we do E1 cross E2 equals to k. These should be vectors. So looking at the directions, we have x hat and negative y hat. So we see x hat and we see negative y hat. This is E1, this is E2. And then we know that k is, like we said earlier, coming out of the page in the direction z. So, right, we can denote this here, but I just have it denoted on the side for clarity's sake. Now, if we try our right-hand rules on this plot, right? Our index finger goes in the direction of E1, our middle finger goes in the direction of E2. We find out that using the right-hand rule, our K would actually be going into the page, which is contradictory to what we know beforehand, right? Our K is in the z-hat direction. It's the positive z-hat direction. So it can't be that. So the right-hand rule isn't working. So then let's look at it from the left-handed perspective. So using our left hand, index finger points in the x direction, our middle finger points into the negative y direction. We end up getting our thumb is pointing out of the page, right? Denoted like this, which ends up matching what our K should be. So this ends up telling us that it is left-handed, right? We know from beforehand that it's elliptically. So it's left-handed elliptically polarized is the type of polarization for this problem. Now that we have finished part 3, where we've determined the polarization, we can now find the H field, again using this kind of same plot. So now breaking it apart and looking at each E field individually, we have E1 is pointing in the X direction. We still have K pointing in the Z direction, but we need to find H. So this cross product formula changes slightly. We have E cross H equals K. So we know E, we know K, so we can find H. So our index finger points in the direction of X, which is our E. Our middle finger, we don't know where it goes yet because we do not know H, but our thumb is coming out of the page. Right. So orienting your thumb and your index finger, you end up finding that our middle finger points straight up, or in the Y direction. So H1 is pointing in the Y direction. That is the direction for the first H field. I will denote this to the side here. H1 equals Y hat. Now we need to do this for the second part of the E field, right? The initial direction is in negative Y hat. So negative Y hat. This is our E2. And our K hat is still in the same direction. It is still going out of the page. So pointing our index finger down, pointing our thumb in the direction of K, which is coming out of the page, we end up seeing that our middle finger points in the direction of X. So our H2 is pointing in this direction. So I'm just going to write this to the side as a quick little note. H2 is going in the direction of X hat. So now we know the directions of our H field, but we still do not know the magnitude. So we need to solve for the magnitude. If we look back up here in the formula sheet, we have the formula here, E naught over H naught equals eta. We can use this to solve for H naught. So E naught over H naught equals eta. But be careful with eta that you do not forget that there is a hidden n in this term. So it should be eta naught over n. This is because oftentimes we are using air, but in this problem we are not. We are using some made-up dielectric material. So we need to rewrite this equation and solve for H naught. We end up getting E naught times n over eta naught is equal to H naught. Now we know all these terms. Eta naught is just the 377, as we know from class. So we can solve for the amplitude of our H field. So looking back up, we have an amplitude of 2 for the first part, so let's go with the first part of the H field. So H naught 1 is equal to E naught, which we just said was 2. Our N, which we found when we found the dielectric constant, was 1.73. So 2 times 1.73 all over 377. Now, solving for this, we end up getting a very small value of 0.0012 amps. We know this is amps because the initial E field has volts, so our H field needs to be in amps. But we're actually going to end up converting this to milliamps, so multiplying this by 10 to the 3. Oh, it's not 1 here, it's actually 9. 0.0092. So when we end up converting this to milliamps, we end up getting 9.17 milliamps. Okay, and now to find the second amplitude of the H field. The only difference between the first one is that our original amplitude of the second part of the E field was 1. So it's 1 times 1.73 divided by 377. So it should end up being half this first answer. We end up getting a value of 0.0046 amps, which ends up converting to 0.4, It should be the opposite. It should be 4.58. 4.58 milliamps. Now that we have the direction, the amplitude for all of our H field, we can now combine it all together. So let's do this first. We will solve for the entire first H field, so H1. H1, first we write its direction, which is in y hat. Then we write out the amplitude, which is 9.17. And then it should be the same cosine term as in the original problem. So it's cosine 10 to the 8t minus z over square root of 3. It should be identical. So cosine 10 to the 8 t minus z over, I do not want to confuse my fraction with that subtraction sign, so it's square root of 3. And make sure that the units have changed, so it is milliamps per meter. This is our H1. H2, it follows the same process. We first grab its direction. Its direction is an x hat, so we write x hat. Then we need its amplitude, so it's 4.58. And then it should be the same thing with how H1 is still cosine, the H2 should still be sine. It should be the same as the original second part of the E field. So we have sine times, or in the parentheses, 10 to the 8t minus z over square root of 3. And yet again, we need to have the units, so milliamps over meters. And now the problem does say the corresponding H field. We can combine these two H fields into one, so we can write H tot. Right, the total H field is equal to H1 plus H2, which would just be combining these with an equal sign, but it is the same answer nonetheless. And with that, we have solved for the entirety of this problem. and all 4 parts. Thank you.